So now we are already familiar with the different causes of the occurrence of Prestress loss that the code wants us to consider when computing the magnitude of the effective prestressing force. So now, let us discuss all of those causes individually. So let us start with the elastic shortening of concrete, which is usually designated as ES, elastic shortening of concrete. So what is elastic shortening of concrete? Concrete shortens when a compressive prestressing force is applied. As the tendons that are bonded to the adjacent concrete simultaneously shorten, they lose part of the prestressing force that they carry. So that is the main reason why prestress loss occur when the concrete experiences shortening. So when the compressive force or when the prestressing force is transferred by the prestressing reinforcement to the concrete element, the tendency is the concrete is being compressed, thereby experiencing what we call shortening. And since the prestressing reinforcements are bonded to the concrete that covers it, when the concrete that covers the or that is bonded to the prestressing reinforcement experiences shortening, the the same scenario is being experienced by the prestressing reinforcement, and because of that shortening, because of that scenario, the prestressing reinforcement tends to lose part of the prestressing force that uh, that is being carried by it. So that is the reason why prestress loss due to elastic shortening of concrete occurs. So again, when the prestressing force is transferred from the prestressing reinforcement to the concrete element, the concrete tends to experience or the concrete tends to be compressed, thereby experiencing what we call shortening. And because the prestressing reinforcement is bonded to the concrete, the shortening that the concrete experiences will be also experienced by the prestressing reinforcement. And because of that shortening that is being experienced by the prestressing reinforcement, it loses part of the prestressing force that it carries. So to illustrate the different way, or to illustrate the way or the method to compute for the magnitude of the prestress loss due to elastic shortening of concrete, let's start for the case of pretensioned elements. So let us just recap the the setup for pretensioning. So it looks like this. So this is the stage wherein the prestressing reinforcement is already cut. Therefore, the prestressing force is now being transferred to the from the prestressing reinforcement to the concrete element. So you can see here that the concrete element is still fully supported all throughout the length. So let us just call the length of the concrete element, say for example, length L. So let us just call the length of the concrete element as length L. So when the prestressing force is transferred to the concrete element, again, take note of this. The prestressing force that is being transferred to the concrete element is not actually the is not actually equal to the jacking force itself, but a a a magnitude of uh, a magnitude lesser in value compared to the jacking force itself, because as we have discussed before, from the time of jacking to the time of transfer, the prestressing reinforcement experiences what we call relaxation. That is actually another cause of prestress loss that will be discussed further later. And because of that relaxation, the the prestressing reinforcement tends to lose part of the prestressing force that it carries. So usually we designate the loss due to that relaxation as equal to this expression here, delta p sub r, from the time of jacking to the time of transfer. So you can expect that the actual magnitude of the pre-stressing force that is being transferred to the concrete element is not actually equal to the jacking force, but a value or magnitude lesser in value compared to the jacking force. So when the pre-stressing force is transferred to the concrete element, the tendency is the concrete element will tend to bend upward, thereby experiencing what we call camber. And when it already experienced camber, it will now behave like a simply supported beam, thereby forcing it to support its own weight like this. So again, in that case, when the pre-stressing reinforce, I mean the when the pre-stressing force is transferred to the concrete element, it compresses com- the concrete, thereby making the concrete experience what we call shortening with a total magnitude of, let us just call the total magnitude of that shortening equal to delta ES, shortening due to elastic shortening. Uh, I mean deformation due to the elastic shortening of concrete. So if we will just divide the total shortening equally from both ends of the concrete element, we can say that the amount of shortening experienced by the concrete on this side is just half of the total shortening, and same magnitude that it will be experienced on the other end. So if you will just sum up the total shortening be experienced by the concrete, it will sum up to delta ES. If you will just multiply this by 2, since there are two of them present here on the illustration. So when the concrete element shortens like like this, when the concrete element shortens like this because of the compressive force applied by the pre-stressing reinforcement, uh, actually the concrete element experiences again what we call elastic shortening, and because of that, it loses the pre-stressing reinforcement loses part of the pre-stressing force that it carries. And when it already lost part of the pre-stressing force that it carry starting from this magnitude, the resulting magnitude of the pre-stress force when you already deducted the pre-stress loss due to the elastic shortening is now what we call the initial pre-stressing force. So that is actually the magnitude of the force that we usually use for the computation of the stresses acting on the concrete element starting from the initial pre-stressing at transfer to the initial pre-stressing at transfer with self-weight. So that is actually the magnitude of the pre-stressing force we usually use on those computations. And again, that is the pre-stress force that resulted when you deducted the pre-stress loss due to the elastic shortening of concrete to this magnitude of force that is actually being transferred by the pre-stressing reinforcement to the concrete element at transfer stage. So if we will investigate the two materials here, the concrete and the pre-stressing reinforcement, let's start with the concrete. We will investigate what happens to the concrete when the concrete experiences elastic shortening of concrete. So we can recall from mechanics of four mobile bodies that strain is equal to deformation over length. So in the case of the concrete, the the deformation or the strain that is being experienced by the concrete, let us just call it as strain sub ES, strain due to the elastic shortening of concrete. And that is just equal to the deformation of the concrete, which is the delta ES here, the total deformation, divided by the total length of the concrete, which is L. So that is the equation for the relationship between the strain, the actual deformation, and the length of the concrete as it shortens. And then, since we assume from the very first discussion that our concrete at this particular stage of pre-stressing operations, we assume that our concrete is still elastic. Therefore, it still satisfies the equation for Hooke's law, which just states that the stress is just proportional to the strain being experienced by the concrete, wherein the constant of proportionality is the modulus of elasticity E. So if we will designate the stress being experienced by the concrete as FCS and the modulus of elasticity being experienced by the concrete equal to ECI, and the strain being experienced by the concrete as the epsilon ES, so we can have this equation. So let's define each of these terms you see here. So FCS, actually this is the stress acting on the or being experienced by the concrete element at the level of the pre-stressing reinforcement. So if you will try to imagine the previous discussions, we know that the stress that we know that the concrete experiences flexural stresses, total fractional stresses in specifically. And the term here that we are seeing here, the FCS, is actually the flexural stress being experienced by the concrete element at this level, at the level of uh, the pre-stressing reinforcement, because we are concerned with the pre-stressing reinforcement on this discussion on the elastic shortening of concrete. And that must be equal, according to Hooke's law, that must be equal to the product of the modulus of elasticity of the concrete. But you have to take note that, again, since we are pretensioning, you have to take note that the modulus of elasticity of the concrete at this particular stage of pre-stressing is not uh, uh, readily equal to the modulus of elasticity of concrete at 28-day uh, compressive strength. Because again, we know for the case of pretensioning that usually the concrete is usually the pre-stressing force is transferred to the concrete even before the concrete attained its 28-day compressive strength. So again, since we know from the previous discussions that modulus of elasticity is actually dependent on the compressive strength of the concrete, so therefore, if there is a different magnitude of compressive strength, therefore there will be a different magnitude of modulus of elasticity. So if we will know what we call the initial compressive strength of the concrete element at time of transfer, therefore we can compute for the modulus of elasticity of the concrete at time of transfer, and we can call that modulus of elasticity as the initial modulus. That is the modulus of elasticity at time of transfer of the pre-stressing force to the concrete element, which have a compressive force or compressive strength equal to FCI prime. So if we know the value of FCI prime, we can compute for this magnitude, the initial modulus of elasticity. And again, according to Hooke's law, this stress here must be equal to the product of the modulus of elasticity and the strain being experienced by the concrete, which is obviously equal to this, the term that we have computed a while ago. And again, we know that strain is just equal to the deformation over length. And we can see here on the illustration that the deformation that was experienced by the concrete element when the pre-stressing force is transferred is just equal to the sum of these two deformations here, which just equals to delta ES. If you will just divide that to the total length of the concrete element, you can already find the strain being experienced by the concrete, which is this. So that is for the case of concrete. Although we can also express this in terms of strain ES, which must be equal to this. So we just bring down uh, the ECI on the as the denominator of FCS. So that's why we had this expression here. So that is for the case of the concrete. Now let's talk about the behavior of the pre-stressing reinforcement or the pre-stressing tendon. So again, just like the concrete, we know that the pre-stressing reinforcement is also elastic at this particular stage of pre-stressing. So therefore, it must satisfy Hooke's law. So the stress being experienced by the pre-stressing reinforcement must be directly proportional to the corresponding strain it experiences. Or in equation form, if we will signify the stress being experienced by the pre-stressing reinforcement as it shortened from this form to this form, let us just call that delta FPES. So the pre-stress loss due to the uh, elastic shortening of concrete. And that stress must be equal to the product of the modulus of elasticity of the pre-stressing reinforcement, EPS, times the strain being experienced by the pre-stressing reinforcement. And you just have to take note for the case of the strain being experienced by the pre-stressing reinforcement, you just have to take note that since since the pre-stressing reinforcement and the concrete uh, are already bonded together. Therefore, the pre-stressing tendon suffers the same magnitude of shortening as the concrete. So meaning, if the concrete experience a deformation equal to this, the sum of these two, therefore, the pre-stressing reinforcement will obviously experience the same magnitude of deformation, or in other words, they will both have the same magnitude of strain. Therefore, the strain being experienced by the pre-stressing reinforcement that is specified here on this equation, which is this, is just equal to the strain being experienced by the concrete element, which is equal to this. Therefore, we can substitute this expression in place of this. So if we will try to substitute that, we will have this equation here. Or if we will just try to express this ratio of the corresponding modulus of elasticity of the pre-stressing reinforcement and the concrete itself, let us just signify or designate that ratio as the variable n, which is what we call the modular ratio. That is just the ratio of the modulus of elasticity of the pre-stressing reinforcement and the concrete element. So if we will designate it as the modular ratio n, bring down or and then uh, retain FCS, therefore we can find the formula for finding the pre-stress loss due to the elastic shortening of concrete, which is equal to this expression. So how can we find FCS? So if you can remember, how can we find total stresses acting on concrete element at this particular stage of pre-stressing, which is the initial pre-stressing at self-weight? If you can remember, this is the uh, flexural stress diagram, the total flexural stress diagram acting on the concrete element, specifically at the midspan. So this is the formula for the extreme flexural stress at the top, and this is the formula for the extreme flexural stress at the bottom. And this is actually the total stress or total force, total of the several flexural stresses that you see here. So if we want to find the corresponding flexural stress acting on the same level of the pre-stressing reinforcement, we can use the formula below. Since the pre-stressing reinforcement uh, is located below the centroid or the neutral axis of the concrete element. So again, or in other words, since the pre-stressing reinforcement is located at the pretension zone of the concrete element, we can use the formulas for the stress acting on the pretension zone, which is this. So again, may I just recap? The FCS that we are specifying here is actually the flexural stress or the stress being experienced by the concrete, which is this, but specifically on the level, which is this, of the pre-stressing reinforcement. So we have to find this particular magnitude of stress acting on the level of the pre-stressing reinforcement. And how can we find that? So if we are in the stage of initial pre-stressing at transfer with self-weight, specifically at midspan, we can use this formulas. But since the pre-stressing reinforcement is located on the pretension zone, so again, what is the pretension zone? It is the zone on the concrete element which experiences tension as the concrete supports its own weight. So this is the pretension zone, and since the pre-stressing reinforcement is located at the pretension zone, we can use the formula for the stress acting on the pretension zone, which is this F sub t. So we can use this formula. We just have to change the magnitude of C, because as we all know, C stands for the distance from the centroid or the neutral axis to the fiber that we are considering to find the flexural stress. And since this is the location of the fiber that we are concerned, which is at a distance E from the centroid or the neutral axis of the concrete element, we just have to replace the C that you see here as equal to the eccentricity E. So if you will try to substitute that, you can find this equation for finding the stress acting on the concrete at the level of the pre-stressing reinforcement. So that is the formula for finding that the stress acting on the concrete at the level of the pre-stressing reinforcement. So the P that you see here for the computation of the stress acting on the concrete at the level of the pre-stressing reinforcement, the P that you see here is actually equal to this expression. The actual magnitude of the pre-stressing force that is transferred to the concrete element at transfer. So again, we all know that that magnitude of pre-stressing force that was actually transferred to the concrete element is not actually equal to the jacking force itself, but equal to a certain magnitude, certain value that has lesser value than the jacking force. Since we all know from the previous discussions that from the time of jacking to the time of transfer, the pre-stressing reinforcement experience what we call relaxation, thereby producing what we call pre-stress loss on the pre-stressing reinforcement. So that is the magnitude of the P that we will use here in order for us to find the stress acting on the concrete at the level of the pre-stressing reinforcement. Although uh, the M here that we will use will still be the moment due to the dead load alone, the self-weight alone, since we all know that at this particular stage of distressing, the bending moment acting on the concrete element along the length of the concrete element, specifically at midspan, is just equal to the moment due to the dead load, because that is the only load that is being carried by the concrete element. That is the only transverse load that is being carried by the concrete element. So the moment that you will use here will just be coming from the moment due to the dead load being carried by the concrete element. Although you just have to take note. Although you just have to take note that the P that you see here, the P that you have to use for the computation of the stress acting on the concrete at the level of the pre-stressing reinforcement, the P that you see here can be approximated as equal to the jacking force, or if we can approximate this P as equal or approximately equal to the jacking force, meaning we can assume that relaxation, the pre-stress loss due to the relaxation of the pre-stressing reinforcement is approximately equal to zero. Therefore, P is just approximately equal to PJ. We can estimate the magnitude of P equal to that. We can approximate it approximately equal to the jacking force itself. Or for safety purposes, we can assume that this pre-stress loss due to relaxation of the steel or the pre-stressing reinforcement is just 10% of the jacking force. Therefore, the remaining force on the pre-stressing reinforcement after the occurrence of this relaxation will be just equal to the 90% of the jacking force. So we can assume this here, what you see here, we can assume this if we don't specifically know the magnitude of this particular loss, which is the relaxation of the pre-stressing reinforcement. So that is how you can compute for the uh, elastic shortening of, that is how you can compute for the magnitude of the pre-stress loss due to the elastic shortening of concrete.